Okay, so our speaker today is Michael Schapira. He's did all his degrees at Hebrew University and then came to the States. Your advisor was Noam Nissan. He came to the States and has worked at Berkeley and Yale and Princeton and is now working as a developer at Google, actually implementing the stuff that he actually studies. Which is a great example to all of us, and he's going to talk to us today about when it is best to best reply.
Thanks for the introduction, and this is based on joint work with Noam Nissan, Gregory Valiant, and Aviv Zohar, who's over there. So, a few words about the structure of the talk. I'm going to start by talking about the original motivation for this work that comes from internet routing. And I will then describe the model, what we mean by best response mechanisms, and specific applications to auction environments. So, internet routing. The internet is made up of smaller networks called autonomous systems. They're owned by different economic entities, AT&T, QS, Comcast, Verizon, and so on. And currently, routes between these smaller networks are established by the Border Gateway Protocol, or BGP. So BGP is a very crucial part of the internet infrastructure. It can be regarded as the glue that holds the internet together. Oh, of course, if you have questions, just feel free, whenever. So why isn't this trivial? Well, the reason it's not trivial is because, like I said, these different networks are owned by different economic entities with very diverse, often conflicting goals. So the ASs might be interested, ASs are these small networks, they might be interested in maximizing revenue by transiting traffic for customers. They might be interested in avoiding paths through certain other ASs. They might just have more standard preferences, like preferring shorter paths to longer ones. But the thing is, they have very different preferences. This is truly an economic environment in that sense. So let me say a few words about the formal model for BGP routing, because that is going to be one of the examples of a best response mechanism. So the way that BGP works is that routes to every destination network are computed independently. So without loss of generality, when you think about the formal model, you can think about a network graph where the set of nodes, the set of vertices, consists of n source nodes, 1 to n, and all of them wish to send traffic to a unique destination node D. So we have a unique destination node, and everyone wants to send traffic to D. And the set of edges, or links, L, represents the communication links between these nodes. So each node is one of these networks we've seen in the previous slide, and communication links between these are captured by the edge set. So what's BGP? BGP is this, at a high level, very simple protocol. Obviously, if you dive into the technical details, it gets quite complex, but every source node has private preferences over all possible simple, and by simple I mean loop-free routes, between itself and the destination D. And each source node is requested, or the prescribed behavior is for each source node to repeatedly execute the following actions. First, receive all routes from your neighbors. So my neighbors announce which route to D they're currently using. Choose the best route, and by best I mean the route you like the most given your private preferences. And then announce your newly chosen route to your neighboring nodes. So here's a very simple illustration of how BGP works. Think of the network where you have a unique destination node, D, and you have two source nodes that wish to send traffic to D, 1 and 2, and they have private preferences over routes. So say 1 actually prefers the indirect route over 2 to the direct route to D, whereas 2 prefers the direct route over the route through 1. So now what we have is an asynchronous interaction between these nodes. So first, the destination announces itself. It actually announces itself to both nodes, but this is an asynchronous setting, so it could be that one learns about this after 2. So 2 gets a message from D saying, hey 2, I'm available. And for lack of other options, it selects the direct route to D. Next, it announces to 1, I'm using the route to D. And in BGP, nodes actually announce the entire path to the destination. So it announces the route to D, enabling 1 to get a route through 2. Now let's say that the message from D to 1 is finally released. So 1 now knows that it actually has 2 options. It can go through 2 or it can go directly to D. What will happen now? Nothing, right? Because 1 does not wish to change its route, and neither does 2. And even if 2 did want to go through 1, it wouldn't be able to because 1 is already going through 2. So 2 has no other available route but the one it has. So the point is, this is what's known in networking literature as a stable state. And the hope is that BGP eventually converges to such a stable state. So one challenge, an obvious one, is how do we even know that this will happen? So how do we even know that BGP will eventually converge to a stable state? This is a very active area of research in the networking community, because if you don't converge to a stable state, what you're effectively doing is both making the network unpredictable and flooding it with update messages because your route keeps oscillating. This is actually worse than standard questions in say, game theory about these things, because the network is inherently asynchronous. That is, I could be activated at the same time as another node, update messages are delayed, like everything bad that could potentially happen might potentially happen. That didn't make sense, but yeah. Second challenge, which is the second challenge, which is going to be the main focus of this talk, is why should a source node even execute BGP? So we're assuming that everyone follows this prescribed behavior. But each node can decide whether or not to follow this prescribed behavior. And the question is, if a long-sighted node can improve its own routing outcome by doing something else, who knows what? Maybe optimizing something, always choosing the second most preferred route, who knows? But if it can optimize its outcome by doing something else, then surely it will do so. And like I said, so this is a very active area of research. In this talk, I want to focus on the second challenge, the incentive question. Any questions so far about BGP or anything else? So first of all, is there a reason for concern? That is, why shouldn't BGP be incentive compatible? And the reason it shouldn't be incentive compatible is that normally protocols aren't incentive compatible. Like as a rule of thumb, your average internet protocol is not. And one famous example is actually the other standard universal internet protocol, which is the TCP, which handles congestion control on the internet. So if you're not familiar with TCP basically is a protocol that dictates how source nodes should adapt their transmission rate so as to not congest the network. And the basic idea is that as long as I can send more, I do send more. But as soon as I encounter congestion, I back off very drastically. I decrease my transmission rate by quite a bit. And this is the very essence of a protocol that's not incentive compatible, because if I know that everyone else is doing this, if I know that they're decreasing their transmission rates at the same time, then I can take advantage of all this unused bandwidth by just sending as fast as I can. So TCP is not incentive compatible, it's BGP. And it turns out that, surprisingly, in realistic environments, BGP is incentive compatible. So I want to just say a few words on what that means. What it means is that if I'm interested in getting as good a route as I can based on my own private preferences, and I know that everyone else is executing BGP, the best thing for me to do is to also execute BGP. I will never get a better route by doing anything else, no matter how sophisticated, no matter how complex.
But this is like a repeated game setting.
This is a repeated game setting. That's true.
Use threats and everything to...
Ah, good point. Okay, that's a very good point. It's a repeated game setting, but you cannot use threats. Like, if there's one thing that's obvious, is that if everyone else is using BGP, they're not all going to change their configuration to punish me because I did something that was not okay. And plus, they're probably not even going to notice because it's not entirely sure. They have no way of knowing exactly what I do. So the basic assumption here is that they are executing BGP. It's not as if they're going to deviate from the protocol to punish me because they know I've done something wrong. And I think for internet protocols, that is the only reasonable assumption. No one's going to change their configuration because some node on the other side of the internet did something bizarre. So when I say incentive compatible here, what I mean is this. I mean unilateral deviation from this specific strategy, from BGP, is not worthwhile for you. So that brings me to the, unless there are questions about the previous part, that brings me to the more general question that we ask. So let's step back from BGP. What is BGP? BGP is just one special case of best response dynamics in game theory. So best response dynamics is arguably the most natural procedure for reaching a pure Nash equilibrium in a game. Basically, you start at some arbitrary action profile of the players, and you repeatedly allow players to best respond to the other's actions. That is, to choose actions that maximize their utility given what the others are currently doing. And this goes on, hopefully, until a stable state, which has to be a pure Nash equilibrium of the game, is reached. And an observation is that intuitively, BGP is best response dynamics in a specific class of routing games. And the reason is, what does every router do? It looks at its neighbors, selects the best route it can at the moment. Then when it activates again, it does the same thing. So best response dynamics in computer science terms captures greedy behavior, essentially. And this intuition was made formal in two different papers.
I have a question.
Yes.
Why is the stable state only the pure Nash? Just by
Yeah, because basically, what's a pure Nash? It's a state that is the best response of each and every one of the players. That is, when you're at a pure Nash, no one has incentive to move.
And so...
So as long as people are best responding, the only way for them to stop is if they reach such a state from which no one wants to move.
So why not mix Nash?
Because here we're talking about pure strategies.
Okay.
As in BGP. That's the reason. Because you're moving between pure strategy profiles.
But you're talking best response to your neighbors. Okay, can you explain the information?
You mean in BGP?
In whatever you're talking about, best response.
So right now, think of the classical best response dynamics environment. So you have strategies, right, and you're just reacting to everyone. Like in the specific BGP scenario, you have to add a lot of details. You're right, because it's your neighbors, and it's asynchronous, and the knowledge propagation is not. But right now, for the purpose of this talk, just think of like perfect monitoring, everything like the standard setting. Yeah.
I think this might be too far afield, but I wanted to follow up on his question on mixing after. In terms of making sure things converge to a stable state, which is the thing we're not talking about now.
Right.
A lot of the strategies in other distributed computing things, which use randomized algorithms, that avoids, impossible results.
Mm-hmm.
So, is there some connection to that here?
You mean in the BGP context?
Yeah, like to use mixed strategies in order to ensure convergence.
So at least in the BGP context, but I think it extends to other contexts as well. The reason you would not want to use mixed strategies and reach a mixed Nash is precisely because it's precisely a contradiction of why you would want to get stability in the first place. Because stability in that context really means getting an action and sticking with it. Whereas if you were playing something mixed, your route would oscillate because of what you're playing, because you would be choosing this with some probability and that with some probability. So you would you would have to keep updating your neighbors about changes in your route and so on. I don't know if that answered your question. Yeah.
Is it guaranteed that the pure Nash is reached somehow?
You mean in general in best response dynamics? No, it is not. So there are many games where...
I know. So here, I mean, you said hopefully you can reach such a...
Yeah, if one exists and best response dynamics can converge to one, then you would reach one. But it doesn't happen in any
So
game.
far we haven't talked about the prerequisite for it to converge, right?
And we will not.
Okay.
We haven't because in this talk, I'm going to look at very specific classes of games where I'm guaranteed that they converge, but there's really only the incentive question. Okay, they converge, but should I be repeatedly best responding? So
is there an easy reason why it is will converge?
There are all sorts of examples in game theory literature. Maybe one famous one is potential games, where every time I best respond, I also improve some potential function, so we reach the optimum of that, a local optimum at least of that potential function. But there are many techniques and many different classes of games. Any more questions? Yeah.
The action space is choosing a path, and it's automatic that your path is announced?
Forget about BGP for a while, but yeah, in BGP it could either be choosing a path or choosing your next top neighbor, depending on the formulation. And right now I'm not looking at asynchrony or convergence, so just assume perfect knowledge. Like when I choose some guy, I have a consistent worldview with him. But I'm not going to talk about BGP again. That was...
So the path that you, for the route that you chose and your declared route are the same?
Exactly. Exactly. They don't... Right. So in real BGP, I would be choosing something and then announcing something, but by the time you get my announcement, I might choose a different route. But forget about these complexities for now. And they don't affect the question that I can. Okay, so under best response dynamics, the prescribed behavior for each player is basically greedy optimization. But is this rational? That is something somewhat surprising in game theory and economics literature is that often best response dynamics is assumed without strategic justification. But if the players are rational and they can benefit from not doing this, then why don't they deviate from best response dynamics? That's the essence of this talk. So specifically, when is it true that a long-sighted player cannot gain by doing something else, given that the others are repeatedly best responding? Like a way to think about this is, we want best response dynamics itself to be an equilibrium. We want it to be such that no one has incentive not to do it. Is this, in the BGP context, the motivation is obvious. Everyone is running the protocol, I also should be. Right? So here's a simple example before I go into the details of the model for why this is problematic. So think of this 2x2 simple game. We have the blue player, he's the row player. We have the red column player. The payoffs are in blue and in red for the respective players. And the arrows represent the best responses. So for example, if I'm here, then the blue player wants to take me here, right? Because his payoff is higher here. On the other hand, the red player wants to stay, because his payoff here is lower, right? So this game has everything we could hope for in a game, basically. It has a unique pure Nash. It's even Pareto efficient. It's a potential game. It is dominant solvable, everything. And yet, the problem arises even here. Say that the starting position is this. What should the blue player do? Like, look at the world from the blue player's perspective. If the blue player knows that the red player is repeatedly best responding, what should the blue player do? Stay there, right? If it does not stay there, then we'll know where he's going to end up. He's going to take us here, and then the red player will take us there. But if he does stay here, then he gets a higher payoff. So this is kind of discouraging, because it means that even if we look at a very specific, very restricted game, we already don't have that best response dynamics are incentive compatible. But don't be discouraged, because there are going to be interesting examples as well. And BGP is going to be one. Questions?
wasn't it the case that in potential game, what is the rule in potential games and best response dynamic?
What do you mean by the rule?
Doesn't best response dynamic work well in potential game? I guess not. Right?
It always converges,
Always converges.
but it's not,
not
as this
the
example
equilibrium
shows,
set.
it's not incentive compatible. That's actually the heart of the point.
Yes.
You might converge, but it might not be rational for you to even do this. So here's the model. You get a one-shot game, the standard one-shot game, like the one we've seen. I'm going to call strategies here actions because I don't want to confuse it with the dynamic interaction. So n players, each player has an action set, a sub I, a private type. In the BGP context, you can think of this as the preferences over routes, but some private type that distinguishes it from others, and the utility function, which is a function of the types and the actions. So far, the standard game theoretic environment. Now comes the dynamic interaction. So infinitely many discrete time steps and some initial action vector where we start. One player is activated at each time step. We will not actually need this assumption, but think of it as if we're just activating them in some cyclic round-robin order. It's going to make everything much simpler. The results are not actually dependent on this. Now, player strategies in this game specify what they do at each and every time step when they're activated. And that could depend on the history. It could be complex. It could be anything. The point is that repeated best response is just one thing you could do here. Repeated best response is the strategy in this game where you repeatedly best respond, right? Where every time I just look at the current actions and I do the best thing for me now. I behave greedily. And best response dynamics is the strategy profile in which everyone repeatedly best responds. Any questions about this slide before I move on? Sort of the...
But every player knows or cares only about his type, you said, right?
Every player
Cares only about his type.
yes, and only knows his type.
Yes, yes.
Yeah.
So
Like
there's
that.
no aspect of learning.
There's no
Even
aspect
though
of learning.
After I've observed
No.
the process for a long time,
No.
I can start figuring out.
And
what
the
the-
guarantee actually has to make it so that learning would be insignificant. So I didn't get to that, but it's going to be an ex post match in the sense that even if I don't know your type, but I know that you're best responding, you might be best responding based on whatever type you have. It should still be the best thing for me to best respond. So in that sense, I don't even need to learn your type. I know that it's the best thing for me to do. So what I didn't define is the payoff in this extended game. So one option is a learning equilibrium approach. So that's a concept presented by Brockman and Terenholz. You can think of a model where basically what I get is the average payoff over time, like whatever my payoff converges to. But since it doesn't necessarily converge to anything, you can think of the limb soup of that sequence. And you can have many alternative formulations with discounts and whatever. The other is the payoff at the limit model, which says if we do converge to something, I get the payoff at that something. If we don't converge, everyone is penalized. And both models make sense in different contexts. So this is definitely much more appropriate for BGP-like environments because there's no start time and no end time, so I should really be thinking about like dynamic interaction over time. In an economic mechanism design context, this does make sense because you can think of it as if there's a mechanism that waits for the system to converge. If it doesn't converge, no one gets anything. If it does converge, it just outputs whatever it is that we've converged to. So to summarize, two models. One is just over infinitely long time, the average payoff for each player. The other is either you converge to something, in which case that's your payoff, or you don't converge, in which case I punish you somehow. So what do we want? We want to identify classes of games in which best response dynamics are in ex post equilibrium. So this relates to what you said. So basically, best replying is incentive compatible in the following sense. Regardless of what my private information is, regardless of what your private information is, if you are best responding, I should be best responding. There's nothing better for me to do than to repeatedly best respond as long as everyone else is doing this. Now, we've just seen an example of a very small game where this does not apply, and that already tells us that if there is such a class, it's going to be extremely, extremely restricted. The interesting thing is going to be that many interesting applications fall within these classes that we're going to identify. So this brings me to question?
Can you repeat in what sense ex post exactly?
Yeah, so ex post means that for every t minus I, for every type of the other guys, for every ti, if all I'm assuming is knowledge of strategy, not of type. That is, the strategy is a function of the type. That is the sense. Back to the BGP context, I don't know what the routing preferences of the nodes are, but I know that for whatever routing preferences they may have, if they're using BGP, I cannot gain by not using BGP.
So when you say for every t minus I, there are two aspects here. One is that the opponents would want to do that given their tribes, right? And is the other also that I would want to do that knowing that this is their tribes? Or you said I don't have to worry about it?
No, for every t minus I.
Given both aspects?
Given both aspects.
Okay.
Yeah, so this is going to be an extremely strong guarantee in that sense. Was that? No? Okay, so best response mechanisms. This is so here's one trivial class of games where clearly best response dynamics is incentive compatible. Let's say that regardless of what the types are, for every realization of the types, you get a game where each player has a dominant strategy. That is, each player has a strategy that he wants to play regardless of what the others are doing. Like there's only one thing in the world that player wants to do, and that's that strategy. So for example, let's say that there are 2 types for each player. So there are 4 possible realizations of the types. And in each of them, we have this kind of situation where the red player wants to play one column regardless of what the other guy is doing, and the blue player wants to play one row regardless of what the other guy is doing. So here, it's simple to see that we are going to get incentive compatibility of best response simply because it doesn't matter what I do. So if everyone else is best responding, they're all going to choose their dominant strategy. Once they do that, I may as well choose my dominant strategy because I have no influence whatsoever on what they do. That's the essence here. So that's a trivial class of games. Unfortunately, I couldn't find any interesting applications that fall within this class of games. We're going to have to look a bit at somewhat broader classes. And this brings me to this superset of the previous class of games, which we're going to call, by the not very sexy name, Never-Best-Response-Solvable Games with Clear Outcomes. So, Never-Best-Response actions are, as the name suggests, actions that are never a best response, regardless of what the others do. So, for example, this thing here, the lower row of that, sorry about this, so the lower row of the row player is a never-best-response action in the sense that if the column player plays this, then this is the best response. If he plays the middle column, then this is the best response. The thing is, you never want to choose this row regardless of what the other guy does. And an NBR-solvable game is a game where if you start removing never-best-response strategies from the game, you eventually reach a single action profile. So maybe the first player removes this strategy. Once this strategy is removed, this strategy becomes NBR solvable, and then there's another strategy, and so on. So this is just a pretty straightforward generalization of dominant solvable games. And clear outcomes, any questions so far? These are NBR solvable games. Clear outcomes are are what we basically need for incentive compatibility. What clear outcome means is that there exists, for each player I, a sequence of iterative eliminations of strategies of the other players, such that if we consider the game after these strategies have been eliminated, then A star is the best thing for that player. It's the optimal state for that player. Let me linger on this slide. So think of the row player. there are NBR strategies of the other players that are independent of the role player. So, for example, let's say that this strategy by the column player is an NBR strategy, a never-best-response strategy. Once all other players, not the role player, remove their never-best-response strategies, when the role player looks at the game that's remaining, the thing that best response dynamics will converge to has to be the place where he gets the highest payoff. Like, what does this capture intuitively? It captures the intuition that other people are going to remove strategies from the game regardless of what I do, because they're never best response. If they're repeatedly best responding, then these strategies are not going to be there. When I look at the world after these strategies are eliminated, because effectively they're not there, then I know that the best thing for me to do is to reach the outcome that would be reached if I just repeatedly best respond. That's the intuition. Yeah?
Are you saying anything about uniqueness here? Because it could be there are many orders.
Very good point. Right now, all of these things are based on an implicit assumption that my preferences are strict. You don't need that assumption. But if you don't have that assumption, you need to specify a tie-breaking rule. Because if I have two best responses, which one do I choose? So I won't go into tie-breaking because that adds a lot of complexity to the presentation. But if you look at the paper, a lot of our results are actually based on very delicate tie-breaking rules. Yeah?
So the column player may remove an NBR column, right?
Yeah.
But how does the role player know which column is he removing so that he chooses?
He doesn't know. This is a property about the game. The game is such that if you start for every player, there is a sequence. Okay.
There is a sequence.
There is a sequence. Okay. I'm not saying anything about the dynamics. This is a static property of the game. Okay. Right? So the dynamics are going to effectively eliminate these, right? But
each term of the sequence depends on the previous ones, right?
Yes. Yes, precisely. Yeah, it could be that the next thing to be removed is this, but it wouldn't have been removed before this was removed. Yeah, that's the iterated aspect of it. Yeah.
But a player has to know some other player's utility in order to, know what.
There's no knowledge here. So think of it as if for every realization of the types, I prove to you that it has this property. It's not that the player knows anything. It's not that he's looking at the other players and thinking, are they going to remove these strategies? It's a static property of the game. The static property is, no matter how you realize the types, it's going to have this structure where for each player there are strategies that can be removed by the other players such that the unique stable state is the best thing for that player in the remaining game.
But if it's done iteratively, so before I decide what I can remove, it's important for me to know what you remove, no?
Right, that's my point.
Yeah, so, yeah, good
So
point.
the question that he asked, I think.
The way to think about this, I think, is you're not deciding anything to remove. So for now, don't think about the dynamics. Okay. Think about the property of the game.
Okay.
The property of the game is there is something that this guy could remove, which is NBR regardless of what you do, such that in what's remaining, this is the best thing for you. Now, by the way, what's the intuition? The intuition is if he's repeatedly best responding, he's going to remove that for you. You don't know what it is, what that thing is. But he is repeatedly best responding, and that's never a best response. So he's going to eliminate that. You don't need to do anything active to eliminate it. That's what's going on. So here's a positive result, whose proof is pretty straightforward, which is if you have one of these games, then first of all, you converge to the pure equilibrium quickly as in the number of players times the total size of the action space, plus best response dynamics are incentive compatible. Now, why are they incentive compatible? Precisely because of the intuition, which is other players are going to eliminate strategies that I have no control over. Once they do that, I'm guaranteed that the unique pure Nash is the best thing in the remaining game for me. So I may as well just repeatedly best respond and get there, because if I do anything else, I might not get there. That's the intuition. So the proof is as straightforward as that. What isn't straightforward is proving for each of these environments that they fall within this class of games. So you need to identify environments and show that they actually can be formulated as these games. So, namely, two internet-related contexts, internet routing with BGP, and congestion control. And also two more economic examples. One is Mulan cost-sharing mechanisms, where you can show, I don't know if you're familiar with the setting, but there's this condition called cross-monotonicity. You can show that if this applies, then it actually implies this game property. The other are special cases of matching problems, like interns, hospitals, and two-sided markets. So what's the general approach? The general approach now, we have a framework for proving that a greedy protocol is incentive compatible. And the framework is, take your environment, formulate it as a game, prove that pure Nash equilibria in your game correspond to desirable outcome, and prove that this game actually falls within our class of games. Both things might not be trivial. Once you've done that, you have a very strong corollary, though. You know that best response dynamics are guaranteed to converge quickly to a pure Nash equilibrium and are incentive compatible. What does that mean? It means that the simplest possible greedy protocol you can think of has these properties. It's incentive compatible and it converges to a desirable outcome. BGP falls within this framework. It can show that it actually pure Nash equilibria are stable states, and it's actually one of these games. Yeah?
I'm getting confused as to whether we're talking about games of incomplete information or games of complete information.
Yeah, so we're talking about games of incomplete information. All of these things, all of these previous, you're right, so that point is delicate. All of these classification of games should think of as applying for any realization of types. No matter how the types are realized, the resulting game falls within this category of games.
So this is a statement then about the complete information game reduced when you
Exactly.
information.
The statement about the partial information game is, for every realization of types, the complete information game you get is within this category of games. That's so yes, partial information, and you're right, everything I talked about so far was complete information.
This might get into details, but how would you prove that the pure Nash equilibrium correspond to desirable outcomes? I mean, that could be very complicated.
And
right?
yes, and it's very environment specific because it's not clear what desirable outcomes mean. So let me actually give you an example where this will arise. So the second example, congestion control. So this looks at the congestion control setting that has been studied in another paper. And basically we have pairs of source target terminals that are communicating over a communication network, where the edges have capacities. So you have a network graph, the edges have capacities, and the game theoretic formulation of this is that each player is a pair of source node and target node. So for example, the blue player is this route, the blue route, so it's the pair of nodes and a fixed route between them. So we have a blue player, a red player, a green player, and the purple player. Player I's action is a choice of transmission rate in some interval between 0 and maximum transmission rate for that player. And his utility is his throughput. By throughput, I mean the amount of traffic that it manages to send across the network from its source to its target. So to fully specify the game, I need to explain how the throughput is calculated, because it could be that we're all sending more than the capacity. So we have to somehow distribute the capacities between us. So here's how the throughput is calculated. For every edge, the capacity of the edge is divided between the different flows whose paths traverse this edge as follows. It's divided equally between all pairs who use the edge. But if someone isn't using all of its capacity share, then the remaining capacity, the unused capacity, is also divided in this way. So in this simple example, we have an edge with capacity 9. We have 3 flows whose routes traverse the edge, blue, red, and yellow, and green. So first, each of them is going to get 3. But the green one is going to leave us with unused capacity, because it only wants 2. So the 1 unit of remaining capacity is going to be equally shared between the other 2. So we're going to end up with 3.5, 3.5, and 2. And this goes back to what you asked. So in this specific context, one definition of desirable outcome are outcomes that optimize some notion of fairness. In this case, you can show that pure Nash equilibria in these games optimize max-min fairness. Max-min fairness, that is, the source who sends the least traffic, the amount of traffic sent by the source who sends the least traffic is maximized. I'm sure that there's a more succinct way of saying that.
I have a question about the model.
Yeah.
Just so when we're dividing these things up, this is how much traffic I report that I want through here, or how much traffic that can actually reach that node given perhaps some earlier thing in the network. Yeah. So can you go back for a second?
Of course.
So in this case, right? So now we know that we can send 3.5
through this edge.
Through this, and then it's going. Say these all arrive at some other node. Then when we divide this up again, am I now calculating based on 3.5?
Yes.
So in this case,
so
I have an incentive to use all my bandwidth then, or no? Oh, no, I'm sorry.
You have some bottleneck capacity, right? If you have a path, it could be that here I can send a lot, but here I'm stuck because I'm sharing this edge with a lot of other flows. So first of all, pure Nash equilibria in these games are interesting. They correspond to things that optimize max-min fairness. Secondly, repeated best response in this context also has a natural interpretation. What does it mean? It means if I'm not sending enough, I should send exactly the bottleneck capacity. I shouldn't send more because that traffic will just be dropped, but I should send as much as I can. If I'm sending too much, I should go down to the bottleneck capacity because my packets are being dropped and this is what I have now. And theorem, these congestion control games, once again, are MDR solvable with clear outcomes. So now we know that this simple behavioral rule for all players is incentive compatible. If all players do this, no one has an incentive to deviate. Any questions about this part before
I assume you're studying non-zero sum game, right? Here. It seems to me there's no way of there is summing up to zero, right?
In some of the games, right?
So I mean, for the pure Nash equilibrium, I mean, Nash equilibrium means that nobody has the incentive to deviate from the equilibrium unilaterally, right?
Right.
But in order to show that it's really desirable outcome, you've got to show that there's nothing like the prisoner's dilemma by both players deviating from the current strategy.
No, so desirable outcome, just think of it as a vague term that you're going to have to specify what that means in the specific context you're looking at. I don't mean that in any collusion-proof kind of sense. So here, in this specific context, desirable outcomes are outcomes that optimize max-min fairness.
Okay.
In this game, that's what we call desirable outcomes. It's going to differ from the basic idea is if I give you an environment, there's something you want to do in that environment. Call that desirable outcomes. I didn't mean to overwrite any notion of desirable outcomes.
Maybe you want to postpone it, but I'm confused now by the question about the type. So even what you say pure Nash equilibrium is not in the standard sense of pure Nash equilibrium, right?
Yes.
Because my I have a pure best response to what their types play. But it does not mean that if I took a distribution over their types, I would still want to do that, right?
Yes, but there is no distribution. That's the ex post sense.
I know, so in that sense it's not this.
Yeah, so let me just say that again, because I might have confused you. So what we're saying is there is a partial information game, right? The types are private. There is an underlying full information game. So if each guy had a realization of his specific type, we would have an underlying full information game. This is the game we care about. If you knew your own and everyone else's. In that game, there's a pure Nash equilibrium. This is what we want to implement.
But you also want it for every such realization.
Yes. So for every realization, I want to reach the pure Nash equilibrium of the realized pure Nash equilibrium. Yeah, of the realized game. So let's look at auction environments now and try to apply the same reasoning. Simplest example, first price auctions. So you're probably all familiar with the setting. we have, let's look at a discretized version of this. So we have bidders, in this case 2, the blue one and the red one. Each has a private value in some predetermined set of integers. And they submit bids in, let's say, the same predetermined sets of integers. The highest bidder wins, and he pays whatever it is he bid. First price auction. Without loss of generality, let's assume that ties are broken in favor of the red bidder. So I want to think about this as a game. So what does it mean thinking about this as a game? Once again, this relates to what you said. To think about this as a game, I need to fix the types, right? Fix the types. Let's say that the value of the blue player, Bob, is 2. The private value for the item of the red player is 4. This induces a game where the bids are the strategies, and in each entry in this matrix tells us who the winner is and what his utility is. If you lose, your utility is 0 because you got nothing. If you win, your utility is your value for the item minus how much you paid for it, which is how much you bid. So for example, here, Alice bid 5, Bob bid 0, so Alice won, but her value is only 4. So her value is 4, but she paid 5, her utility is minus 1. So this is the game. And one famous auction in economic literature is the English auction, the ascending price English auction, which is start at a price of 0 and let the price increase until only one bidder is left standing. If they drop out when their value is exceeded and only one remains eventually, he's going to get the item. So this implements the second price equilibrium because, for example, if there are 2 of us, you're going to drop out when we reach your value, and so I'm going to pay with the price when you drop out. But it's incentive compatible. That's the nice thing about this. Right? So it's incentive compatible for me to just drop out when my value is exceeded, not before, not after. Now let's think about this in the context of this game. So I claim that a specific execution of best response dynamics mimics the ascending price English auction. It's when we start with bids of 0. What happens when we start here? What are the best responses? So right now, ties are broken in favor of the red player, so Bob is winning. Alice wants to win. Her value is much higher than what she's paying now. So her best response is to bid the smallest increment she can possibly bid to win. Now Alice is winning. So Bob, because ties are broken in Bob's favor, wants to match the bid. And this goes on. Right? So they just go up until this guy quits because his value is exceeded. And this is where we're going to implement the discretized second price auction. So we can ask this question more generally, right? So is this a special case of a more general best response auction where you just let them do their thing, start at some initial set of bids, let players best respond until they reach the same equilibrium. And then every auction in this family of auctions will be incentive compatible. And the answer is yes. So this is true. So if you start, for any realization of type, start anywhere, let them best respond, it will be incentive compatible as the English auction is incentive compatible. But you're not prescribing anything, the ascending price behavior, you're not prescribing, so the auction is prescribing very little. It's just basically saying best respond. Unfortunately, to prove this, you can't use the Never-Best-Response-Solvable with clear outcomes rule because it's just not. It doesn't fall within this category of games. So you have to use something else. I'm going to describe this very briefly. Let's present something that might be the strongest possible definition of domination. A strategy set is blindly dominated if the maximum you can get over everything from playing a strategy there is less than the minimum you can get from not playing a strategy there. So it's not just that this is lower than this. It's that this is also lower than this. Right? So here, the maximum here is 4. The minimum here is 5. So this entire strategy set is blindly dominated. So this is a blindly dominated strategy set. And now blindly solvable games are defined in an analogous way. Just throw away these blindly dominated strategy sets until you reach a specific single action vector.
This was done column by column.
Or sets of columns by sets of columns. Yeah, it might be if you have 3 strategies that together the maximum here is less than the minimum here, as in the previous example. So these 2 are dominated by all of these at the same time. So these will be removed, and this might be removed, and so on. So let's revisit first price auctions. They are blindly solvable games. How do I know? Because look at this strategy. Clearly it's blindly solvable. Alice always wins, but it's less than her, she pays more than her value. So the payoff here is -1, the payoff everywhere else is positive. So the maximum here is less than the minimum in the remainder of this matrix. Similarly, that's true for any strategy that is more than your value. You can only lose by bidding more than your value. And now, should Alice ever bid 0? Should she?
That's a breaking in favor of both, so it should never.
Exactly. Alice never wins by bidding 0. Her utility is always 0. So this is blindly solvable. Now that Alice can only bid 1 to 4, Bob also has no incentive to bid 0. So basically, we're mimicking the behavior of the English auction in this elimination of blindly dominated strategies until we reach this specific thing.
Could we run a simulation without the blindly, just by eliminating dominated strategies?
No. Like that. If you recall the first example, the 2x2 game.
No, in this example.
In this example, yeah, every blindly dominated is also dominated. So you could have, but that would not be enough to get you incentive compatibility always. That's the issue. Like you do have dominant solvable games like the one we've seen where you just don't get that. Sorry. So another positive result, once again, very straightforward proof. The thing that is always not straightforward is showing that an application belongs in the class of games. If you fall in this class of games, then you get everything you look for. And once again, the intuition is unbelievably simple. It's because if something is blindly dominated, obviously I'm going to get rid of it. I can never gain anything from playing a blindly dominated strategy because the maximum I can gain is less than the minimum of just randomly choosing something else.
So chess is solvable like this.
Sorry?
So chess is solvable like this.
So chess is incentive compatible for best response?
Could be, right?
And there's an interesting paper there if that's the case. So now,
So both of those theorems were sufficient, but not necessary.
yes. I wish I had something necessary, actually. So now, very briefly, 2 examples that don't fall within any of these classes of games where we had to use ad hoc proofs. And I wish I had the more general theorem that encompasses both, but I don't. So the famous GSP, the famous generalized second price auction that's used for selling like Google AdWords. Basically, you have K slots. Each one has a click-through rate. Users submit bids. They're ranked by the order of their bids, and each one pays the next highest bid. So there's a result by Kari et al. That shows that best response dynamics converge with probability 1 to an equilibrium with the VCG prices. But are they incentive compatible? That is, okay, if everyone best responds, then we'll converge to that equilibrium. Should I best respond if I'm an advertiser? The answer is yes. So it is true in this context that best response dynamics are incentive compatible. Another interesting context, which is also classical in economics, is the unit demand auctions. So you have n bidders, m items, and it's basically matching. Each bidder is interested in just one item and has a value for each and every one of the different items, but he's only going to get one. And here, once again, we present a specific best response auction that is incentive compatible and converges to the VCG outcome. Now here the challenge is different. Like I said, these proofs are ad hoc. And here actually proving the incentive compatibility is very easy. Proving the convergence is much more challenging. and is, like many proofs in the domain of unit demand auctions, it's LP-based and primal dual kind of analysis. So this brings me, unless there are any questions, to the directions for future research. I believe that we've only scratched the surface here. We have no necessary conditions whatsoever, so no characterizations of when this happens. We asked this question in the context of best response dynamics in pure Nash equilibria, but the same question could be asked about any dynamics that have been studied in game theory. Fictitious play, no regret dynamics, and so on. Like, why should a player do this? And any kind of equilibrium. Mixed Nash, correlated, and so on. There are probably more applications out there.
People have to go to class, but for those that don't, we can take questions.
Thanks.
You mentioned the